Okay, fine students. In the last class, we just went through about the derivation for the current in a conductor in terms of drift velocity. Okay, so making use of that, we have derived an expression for electrical conductivity of a material of a conductor. Right. So this was the last question which we discussed in the last class. Right. So now we will start with the 10th question. Okay. So this question that is regarding what is equivalent resistance and obtain the expression for effective resistance of two resistors connected in parallel. So we have come across what do you mean by this effective resistance in case of series itself. So I'll just start with effective resistance of two resistors connected in parallel. Okay, as you know that in the figure you have two resistors which has been connected in parallel. So the current get differs. I mean the current gets split up through each resistor. So the current is different. So the total current comes out to be as I is equal to I1 plus I2. So the next is nothing but the current through each resistor is given by I1 is equal to V by R1 and I2 is equal to V by R2. Adding that you are going to get I is equal to V divided by R1 plus V divided by R2. So that is nothing but equal to I is equal to V into 1 by R1 plus 1 by R2. That is equation 1. So we have taken V common there. So for the equivalent circuit of resistance R, okay, you can write the current as I is equal to V by Rp. Okay, for an equivalent resistor I'm talking. So consider that as equation 2. Compare equation 1 and 2. So the LHS is same. So you can write that as the next step as V divided by R subscript P is equal to V into 1 by R1 plus 1 by R2. So cancelling V on both the sides, you are going to get an expression of 1 by R subscript P is equal to 1 by R1 plus 1 by R2. So this is regarding the expression for effective resistance of two resistors connected in parallel. Okay. So this question can be asked for either for 3 marks or for 5 marks. Okay. So the next is nothing but an important question which they usually ask for 5 marks. Okay. That is nothing but derive the expression for equivalent EMF and equivalent internal resistance of parallel combination of two cells. Okay. So in this question, the 5 mark question which you can expect is one is this regarding the conductivity of a material of a conductor, or else this question 11th one. Okay, so both are important. Okay, so next is nothing but the parallel combination of cells. So in the figure you can see there we have taken the two cells. So E1 is the EMF of first cell and E2 is the EMF of second cell. R1 is the internal resistance of first cell and R2 is the internal resistance of second cell. Okay, as you know that the current is entering from terminal A to terminal B. Okay, so as you know that as it enters this point here in the figure, so the current get split up. Okay, so I1 is the current through the cell 1 and I2 is the current through the cell 2. Okay, so the potential difference remains the same. Okay, so if the two cells are replaced by a single cell, the circuit will be like this. Okay, so E equivalent and R equivalent and I will be the current through it. Okay, so we will start with the derivation, that is the mathematical part of this expression. That is nothing but they have given let E1 and E2 be the EMF of two cells. Fine. R1 and R2 are the internal resistance of two cells. Correct. And I2 and I1 and I2 are the current through the branches of cells E1 and E2 respectively. And I is the net current in the branch AB. Okay, so these are nothing but the explanation of the figure. Okay, whatever we have written there, we have written as E1 I1, so that explanation has been given there. So the next is, as you know that the total current due to this combination of cell is given by is equal to I1 plus I2, which is equation 1. Okay, I is equal to I1 plus I2, which is equation 1. The next is the terminal potential difference across the first cell is, okay. So by making use of the relation as we have just gone through while go through the chapter current electricity, in that we have come across the relation between the terminal potential difference, internal resistance, and the EMF of the cell. From that relation we have taken this equation, that is the equation comes out to be as V is equal to E minus IR. Okay, so since we are applying this to the first cell, so hence we are going to write V is equal to E1 minus I1 R1. Okay, so hence the same step can be written as taking I1 outside, that is towards the LHS. So I1 is equal to E1 minus V divided by R1. Okay, so the next is in the similar way we are applying for the same thing, it has been applied for the second cell. Okay, so the terminal potential difference across the second cell is given by V is equal to E2 minus I2 R2. Taking I2 to the LHS, so we are going to get I2 is equal to E2 minus V divided by R2. Okay, so next, as you know that combining this I1 and I2, we are going to get I is equal to E1 minus V divided by R1 plus E2 minus V divided by R2. Okay, so next is nothing but a mathematical thing. So I is equal to E1 divided by R1 plus I is equal to E1 by R1 plus E2 divided by R2 minus of V into 1 by R1 plus R2. So this is equation 2. Okay, so in this case what now we are going to do is, if the combination of cells is replaced by an equivalent cell of EMF E equivalent and internal resistance R equivalent, then terminal potential difference of that cell is given by, so V is equal to E equivalent minus IR E equivalent. So the value of E equivalent, okay, the value of E equivalent comes out to be as E1 plus E2. Okay, so this equation has been written in this form here. Okay, so where you can see there in the place of E1 plus E2 we have written E equivalent. E equivalent is equal to E1 plus E2, right? So similarly R equivalent is what? 1 divided by R equivalent is equal to 1 by R1 plus 1 by R2. That is what we have written here. We have retained the V. So in the next step you can see it has been given clearly. Compare, I mean from equation 2 and 3, that is comparing, you can write E equivalent divided by R equivalent as E1 divided by R1 plus E2 divided by R2, and 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Okay, so this is regarding the combination of cells in the parallel. Okay, so this is a 5 marks question, so just go through for a few minutes. In case if you have any doubts in any of the steps, you can ask, just go through. Any doubts, students? Shall we move to the next? Okay, fine. See you. We'll move to the next derivation, that is deduce the balancing condition for Wheatston's network using Kirchhoff rules. Okay. So as we have come across the Kirchhoff first law and second law, right? So applying that itself, deduce the we are going to deduce the balancing condition for Wheatstone network. Okay. So you can see this is the Wheatstone network. So this Wheatstone network consists of four resistors. Okay. So you can see P, Q, R, and S. Okay. Between this B and D, we have connected the galvanometer. Okay. We have connected the galvanometer, and this four resistors has been connected in the form of quadrilateral, and it has been connected to a battery of EMF E, and I is the current. Okay. So now you can see here A, B, C, D are nothing but A, B, C, D are the terminals. Okay. So it is said that if the current through the galvanometer is 0, that is Ig is equal to 0, the network is said to be balanced. In this case, galvanometer shows no deflection. Okay. So when do you say that the network is balanced? We say that the network is balanced when Ig is equal to 0. Okay. When the current passing through the, when the current through the galvanometer reads 0 deflection. When does this galvanometer reads 0 deflection? When the potential at B and D remains the same. Okay, when the potential at B and D is same, the current will be 0. Okay, through the galvanometer. So hence the galvanometer shows no deflection at that case. Okay, so now we need to prove this mathematically. Okay, so it is said that at balanced state of network, Ig is equal to 0. Applying Kirchhoff node rule for nodes B and D, we get I1 is equal to I3. Okay. So in this question, it has been given directly. Okay. It has been given directly. So we will go through now. See here. First, what we had done is we have just applied the Kirchhoff node rule for B and D. Okay. What is node rule? Node rule is nothing but it is Kirchhoff current law we have applied. So in this case, so what happens in this case? See, in from terminal, I is the current flowing through the battery. Okay, so I is the current. So when it enters this terminal A, so what happens? The current gets split up into two part. Okay, across the resistor P, I1 is the current flowing, and across the resistor R, I3 is the current. I2 is the current flowing. Okay, so after that, once this I1 current reaches this point B, okay, or the terminal B, so what happens again? That current gets divided. So the current get divided into, like, the current through the resistor Q will be I3, and the current flowing through the galvanometer will be Ig. Okay. So now, as we know that at the balance condition, we said that the current through the galvanometer is 0. So at the balance condition, what happens? Okay, so what is the current rule says? Kirchhoff first law says incoming current is equal to outgoing current, we said, right? So which is the incoming current across the terminal B? Here I1 is the incoming current, and I3 and Ig is the outgoing current. So for a steady state, that is for a balance condition, we said that the current through the galvanometer is 0. So hence here what we are going to write is I3 I1 will be nothing but equal to Ig plus I3. So this is the incoming current, and this is the outgoing current. Okay, so now this becomes 0, so hence I1 will be nothing but equal to I3. That is what I have given here. Okay, so next, the same thing which we apply for the terminal D, that is the Kirchhoff current law. So as you know that I2 is the current flowing through the resistor R. So when this current reaches the terminal D, what happens? The current, okay. So what happens? The current flowing through the at terminal D, just a minute. So see here, I2 is the current flowing across the resistor R, okay, and at terminal D you can see there, okay. So the current which is flowing from the galvanometer joins with that, okay. So now what happens here is incoming current is nothing but we are going to take that one as I2, and outgoing current will be taken as I4 Ig plus I4, okay. So just I'll express here, I mean I'm going to write here I2 will be nothing but equal to Ig plus I4, okay. So this is the incoming current which is equal to outgoing current. So now what happens at the balance condition, the current through the galvanometer is 0, so hence I2 will be nothing but equal to I4. So this is regarding the Kirchhoff current rule which is applied to the terminals at B and D, or else at the node B and D, okay. So next what we have done is, as you can see, I1 is equal to I3 and I2 is equal to I4, that is considered as equation 1. So next what we are doing is, okay, so next what we are going to do is we are applying the Kirchhoff second law, that is Kirchhoff voltage law, to the mesh ABDA, okay. So you can see ABDA is a loop or mesh we call, okay. So now what we need to do is, what does it says, what is the rule to apply this Kirchhoff second law? We are going to consider that the current, whenever we go in a direction of current, okay, whenever we go along the direction of current, the product of current and resistor, okay, will be taken as positive or negative. It depends, whatever you take, sign convention it is left to you, okay. But in this case what they have done is, here they have taken, as we move along the direction of current, the product of resistor and current is taken as positive, okay. So with respect to that, we will derive this. So as you can see, so we are moving along this direction, that is we are moving along ABDA. So since we are moving along the current direction, so the product of current and the resistor is taken as positive. You can see there we have written I1P, okay, I1P. So next we are moving along the direction of, along the direction of current itself, that is from B to D, okay. So you can write that Ig into G, okay. So Ig is the current flowing through the galvanometer, and what you are seeing, that capital G, that capital G is nothing but the, it is the resistance of the galvanometer. So combining that you can write here, but here they have taken directly as 0, since you know that at the balance condition the current through that is nothing but equal to 0, right, through the galvanometer, hence they have left out. Okay, next from D to A, so we are moving along the opposite to the direction of current, okay. You can see the figure, we are moving along the direction opposite to that of current, so hence it comes out to be as minus I to R is equal to 0, minus I to R is equal to 0. So hence that can be written as I1P is equal to I to R, so which is taken as equation 2, okay. I1P is equal to I to R, which is equation 2. Next, in the similar way, we are going to apply this Kirchhoff second law to the mesh BCDB, okay. So applying this KVL, okay, Kirchhoff second law or the Kirchhoff voltage law to the mesh BCDB, okay. So let us start with the B to C, okay. Along B to C we are moving along the direction of current, so hence the product of current and resistor is taken to be positive. That is nothing but we are going to write that as I3Q, okay, I3Q. Next we are moving from C to D, okay. That means that we are moving along the direction opposite to that of current, hence the product of current and resistor to be taken as negative, that is minus I4S. Okay, so next we are moving along the direction of D to B, dB. Okay, we are moving along the direction of dB. So since you know that under the balance condition the current is 0 there, so hence it is directly taken as 0. Minus 0 is equal to 0. So that can be written as I3Q is equal to I4S, which is taken as equation 3. Okay, I3Q is equal to I4S is equation 3. So now what we are going to do is divide 2 by 3. Okay, when you divide 2 by 3, so what happens? Since you have written here, what is that? I1 is equal to I3 you have written, and I2 is equal to I4. So when you divide this equation 2 by 3, what happens? You will be left out with P by Q is equal to R by S. Okay, so you will be left out with the expression P by Q is equal to R by S, which we say that this is the condition for balance of Wheatstone network. Okay, so this is the condition for balanced Wheatstone network. Okay, and even this is an important question which they usually ask. Okay, it is a 5 mark question. So as you know that I have said, the 5 mark question important questions are: one is this one, second is this parallel combination of cells, the last one is this Wheatstone network. Okay, within these three definitely you are going to get one question, okay, out of these three. Okay, so do one thing, just go through for a few minutes. Okay, it is little bit difficult. Okay, so most of the students what they do is they do they take they make wrong in sign convention. Okay, so they consider one, but while writing that, expressing that in terms of mathematics, they'll do it wrong. Okay, they go wrong there. So if one step goes wrong, the entire thing goes wrong here. Okay, so hence be careful about this sign convention. So before just going through this deriving this derivation, please go through the sign convention of that KVL. Okay, just go through KVL and just go through sign convention, then start deriving uh, this derivation. Okay, so go through this expression, that is a Wheatstone network. In case if you have any doubts, you can let me. Okay. Okay, fine. Any doubts, students? In case if you have any doubts, you can ask. Yes, reply. Have you followed the derivations which we went through? Okay, fine. So this is the ending of this current electricity chapter. Okay. So we have gone through 2 marks, 3 marks and 5 mark questions from the chapter of current electricity. Okay. So I think the next is moving charges, right? So do you have that moving charges chapter for your midterm examination? Just check out and tell me. Yes, do you have anyone? Okay, fine. Okay, we will do one thing. So anyhow, we have completed that current electricity chapter, right? So in the next class, we will just go through starting from the 2 marks, 3 marks and 5 marks question based upon the chapter of moving charges. Okay. So coming to the numerical part, I don't know whether I'm going to get a time, okay, to discuss the numerical on the chapters which you have for your midterm examination. Okay. So in case if I get a time, okay, after revising these questions of 3 mark, 5 marks questions, all the chapters which you have for your midterm examination. In case if I have a time, we will just go through. Okay, roughly we will just go through, not in a detailed way. Okay, or else if you don't get a time, so go through by yourself. Anyhow, we have solved all the types of numericals. Okay, from the exam point of view. So you can just go through. In case if you have any doubts, so we will keep a two class. I mean, we will have a two class doubt session on the numericals. Okay, so whatever the doubts you have, you can just get it clarified. Okay, so with this thing I'll just conclude today's class. Okay, so we will discuss these moving charges in the next class. Okay, students.